Hello and welcome to Non-IITian. In this particular lecture, we're gonna start a series of lectures on groups, and the primary intention for this series is to develop a course for IIT JAM 2027. So what we're gonna try is to talk about all the major topics in IIT JAM, be it the complete notions of real analysis, including sequences, series, functions of several variables, and then matrices, finite dimensional vector spaces, and groups. So probably this lecture won't be the first lecture to be uploaded. Probably we will start the series with real analysis, but we are going to start with groups from my side because that is something that is the topic which I like the most. So this is going to be the first lecture on groups, and let us start it. So what we are going to discuss today is what groups typically are, how do they work, and what are the basic intentions we are kind of apply to groups. Okay, so what are groups typically? Okay, so let me just groups. Okay, now the primary goal of mathematics is to generalize objects which are very elementary in nature. Okay, one of the most elementary number system which every child deals with at some point in his or her life are the integers, right? So we know this particular set, which is the collection of all countable numbers in some sense, right? These are the numbers which we primarily deal with. And a very important property of such numbers is the following, that is, if you choose any two numbers from this set, then if you add them up, you still are in this set, right? If you add them up, you are still in this set. Any two integers when added will still result in an integer. If you now the next thing is that how you add it doesn't matter, right? You can add the second two elements first, and rather you can also add the first two elements and then add it to the third element, right? So it won't matter the way you add three elements up. And in fact, this can work for any finitely many elements. So you can have n elements, for example, and you can order them in any way you like. You can suppose you can first add the numbers from a2 to, for example, a5, and then you add a6 to, for example, a8, and then you keep doing that. Suppose at last you add n minus 1 and an. So it doesn't matter the way you order them to add, right? Fine. The next important thing which we can observe from this point of view is that there is a very special number in this set, such that if you add anything to that number, you will get the same number back. So you know that if you add any number to 0, you will get back a. A is any integer, and this works from either side, right? Okay, and consequently we can also come out with the number 0 by adding a number to its negative, right? We can take a number, we can add up its negative to result in 0. Are you getting my point? I hope so, right? And finally, there is a stronger property which is not that general in nature but is eventually seen in integers to be very specific, which is that you can add a number from whichever direction you want, right? So this is a special property. Now let us first name these properties. So this is called the commutative property of integer addition, which we usually call the usual addition. Now this is okay, so we will name these two later, and this is also very famously known as associativity. And this particular operation has also a special name. If you have studied your class, your plus 2 pretty sincerely, you would know that such an operation is what we call a binary operation. Now what we try and do is that we are intended to generalize the notion of integers, whatever is happening inside integers with respect to some operation, to an arbitrary set. Okay, so let us deal with the definition. So let G be a non-empty set. It's essential for it to be non-empty, otherwise you won't be able to do anything. Be a non-empty set. And let star be a binary operation, on G. That is, so star is a function from G cross G to G. That is, if you take any two elements, let's say G1 and G2 from G, then G1 star G2, by convention, and this is the way we denote it. In fact, by the usual notation of functions, we should have denoted it like this. But the better way to understand it in this way, that you are operating G1 and G2 with respect to this particular thing. And so this must be still in G. Okay. So let G be a non-empty set and star be a binary operation on G. We say G with respect to star is a group if the following properties hold. If the following properties hold. And what are the properties? Property number 1 is that star is associative. Star is associative. That is, for all A, B and C in G, if you operate, and it doesn't matter which order you operate them up. Is it clear? Now there are certain structures which is similar to this. That is, you have a non-empty set, you have a binary operation on this, and the operation is associative. Now if I only consider this much of property holding, then we can also name it as a semi-group. And this is in some sense a very essential structure when you talk about, when you are not intended to work with groups, but you are intended to work with more general structure than groups. Semi-groups, and there are also something called semi-rings, and there are semi-structures, a lot of semi-structures. These are more general in fact, but these are not our point of concern at this moment. Okay. So the next property which we require is the following. That is, there exists an element which we usually denote as E in G, such that any element operating with E will result in the same element back, and it doesn't matter from which side you operate it out. Okay. Now again, you might get a structure, a non-empty set with a binary operation which is associative, and this element E exists. So in such a case, we will call the complete structure just a monoid. Okay. But if the final thing holds, that is the point 3, which says that there exists some element B in G, such that I should have mentioned it more. So this happens for every A in G. Okay. This happens for every A in G. Okay. E is a unique element. It does not depend on the elements. It depends on the set itself. Okay. While the third point says that there exists, I should have written it like this: for every element A in G, there exists an element B which depends on A in G, such that A operated with this particular element from any side will result in the neutral element. We often call E to be a neutral element, but we will come to the more conventional name for it. In this case, this BA, okay, we will name it later, but once the third structure hold, we will essentially call it a group. So all we require are these three properties along with a non-empty set on a non-empty set and a binary operation. So if 3 does not hold while the rest 2 holds, rest 3 I would say, including the binary operation, we call it a monoid. And if I also omit point number 2, property number 2, I'll get a semi-group. In fact, if I can also omit property number 1, then I'll result in what we call a groupoid. Okay. Okay, fine. But there is an optional property as well. So let me just write it in a different color. There's an optional property that is for every A and B in G, A operated with B is same as B operated with A, and this is called the commutative property, and we just saw that this is something which holds in integers. It will hold in many groups, but not necessarily in all groups. Okay. Now, if point number 4, property number 4 holds in addition to, in a group, then we call it to be an abelian group. And these are the, I would say, in some sense, these are the simplest possible groups, because there is one famous structure theorem of groups which helps you to characterize all abelian groups up to their number of elements, up to their cardinality. We'll come to that later. That's a very important thing which we deal in groups. Fine. Now let us name these elements one by one, because that's something very important. So this neutral element E is what we call the identity element in G. And these BA elements, these are famously denoted as A inverse, or often, we'll come to this, or often minus A. This is called the inverse of A in G. Now these notations, they are corresponding to how we kind of perceive the operation on G. The operation on G. See, there are basically two ways to perceive the operation on G, so that it's in some sense not that abstract as a group is. Okay. So what we do is, typically we consider the binary operation, or at least the notation of the binary operation, to be the usual multiplication, though it doesn't necessarily mean to be the usual multiplication. We conventionally perceive them to be in some sense the usual multiplication. In that case, A inverse works well. So I'm just saying how do we do that. So in general, this star is perceived as a dot, as you do in multiplication. So A star B, this is perceived as A dot B, more easily perceived as AB. And in that case, once you perceive this as A inverse, what we do in this case is that E is conventionally denoted as 1. Are you getting my point? Because in our general mind notion, we know that A inverse is 1 with respect to the usual multiplication. So that is the convention we generalize into any sort of a group when we are dealing with an abstract group. Is it clear? And on a similar note, if you are also given the liberty to consider this to be the addition, though it does not necessarily mean to be the usual addition, but you can perceive this operation to be addition. And in this case, we know that A plus 0 is equal to A. So in that case, we consider the neutral element to be denoted as 0, and we also know that A plus minus of A is equal to 0. So in that case, that is the reason why we denote the inverse as minus of A. So I hope this is clear. And once we consider a bunch of examples, it won't be more difficult to perceive the operations in the way you want it. So examples. Now one of the examples we have already dealt with while introducing the notion of groups, which is the integers, and you can now work it pretty easily. In fact, Q, R, C, all of these are groups with respect to usual addition. Usual addition, that is the addition we know working on these structures. Secondly, observe that Q with respect to multiplication, the usual multiplication, is not a group. And the reason is pretty simple. See, when we're talking about Q as a group with respect to multiplication, or we are intended to work with Q as a multiplicative group, the identity element would be surely 1, because we know that 1 times any rational number would result in the same rational number, and a rational number times the usual inverse of the rational number would result in 1. So it abides by the definition of identity. So 1 should be the identity here, but there's a slight problem, and the problem is that 0 won't have a natural inverse, right? Because we know anything multiplied to 0 would result in 0. So this is something which abides by, but 0 won't have an inverse. Because if you consider anything to be the inverse of 0, ultimately it would result in 0 and not 1. So therefore 0 has no inverse. 0 has no inverse, and hence we can't include 0 in the structure. But 0 is the only element which causes this problem. So we can essentially remove 0 and the rest of the structure will be a multiplicative group, as we can see. So what we can conclude from here, the third example, is that Q, in fact Q, so we usually denote it as Q cross, which is nothing but Q except the 0 element. And this will be the usual notion to denote element sets except 0 when the sets are something which we already know working with, for example reals and complexes. So Q, R cross C cross are multiplicative groups, and this is a nice exercise you can work with to enhance yourself or to inbuild yourself with the definition of a group. Okay. Now the fourth example would also be very nice. We consider all n cross n matrices over, you can work over Q, you can work over R, or you can work over C as well. So this is the all n cross n, all n cross n matrices with entries from Q, R, or C. Then this particular set, so let me just take it as K. So K can be Q, R, or C. With respect to the usual addition of matrices, is a group. In fact, now I should have mentioned it previously, but I forgot. In fact, this is not just a group, it's an abelian group, because we know that addition is commutative in Q, Z, R, or C. This also forms abelian multiplicative groups. Right? This is also an abelian group because the addition in matrices is multiplicative. And the reason is that we know that in matrices addition takes place component wise, and the components are elements from Q, R, or C, and addition there is commutative. So it should be an abelian group. And this is quite clear, right? Because the addition is obviously a binary operation, because two matrices when added will result in a matrix itself. What should be the additive identity here? It's the 0 matrix. And what should be the additive inverse? You can just take the negative of every element component wise. That will result in the additive inverse. What about multiplication, let's say, is the collection of all n cross n matrices with respect to multiplication a group. Now this isn't a group, and what is the reason behind that? See, if A is any matrix over K can be Q, R, or C, I won't mention it further, then what does it take for this structure to be a group? A must have, there must be an identity element, but there obviously exists an identity element, which is the identity matrix, right? We know that A times identity would obviously result in A. But there is something more we require. See, multiplication in matrices is associative in nature. By its very definition, you can verify it rigorously by the usual definition of matrix multiplication. I'm just writing it out. It is not difficult. So A times B is summation K is equal to 1 to n Aik times Bkj. So this is the way you multiply two matrices. But the second problem is that rather I should write it in this way. Is it necessary that for every A in Mn K, there exists B in M and K such that AB is equal to identity. Now we know from our class 12 level that this is not necessarily true, because for this to happen we know that we are working with square matrices. So in case of a square matrix, if you have something multiplied from its left to get you identity, you will also get something multiplied from its right to get you identity. And that particular element is what is famously quoted as the inverse of A. And we know that every matrix does not have an inverse. For a matrix to have an inverse, its determinant must be non-zero, and every matrix need not have a non-zero determinant. So this is not true in general. Not true in general. For there exists A in M and K such that the determinant of A is 0, and then A inverse does not exist. Right? So what should be our intention to make a multiplicative group structure out of matrices, out of collection of matrices? Now we should do the same thing, right? We should try and remove all the elements which are problematic, come up with the rest of the structure and check whether that case holds in terms of a multiplicative group. And right, so here comes a very important set which is very, very important throughout your mathematics career, which is called the general linear group. So it's called the general linear group, and this is the collection of all those matrices on K such that their determinant is non-zero. So this is the collection of all invertible matrices, and we are done, right? Because identity matrix is an invertible matrix, right? Identity matrix is an invertible matrix, so it is readily inside GLN, right? So IN is inside GLN. Multiplication is by definition associative. Multiplying two matrices will result in a matrix. Is its determinant necessarily non-zero? Obviously, right? Because we know the determinant splits. It's a multiplicatively linear operator. So if you multiply two matrices and take the determinant, it's same as taking the determinant of each of the matrices and multiplying them out. So if both are non-zero, then this is necessarily non-zero. In fact, this is not a general property that product of two non-zero elements will always be non-zero. We'll come to that. That's not something which is necessary at this point. But nevertheless, we know it, right? Fine. So therefore, its multiplication here is closed. It's a binary operation. And since the determinant of each of the matrices are non-zero, we know that for every A here, A inverse exists, and so every element has an inverse, has a multiplicative inverse. So it's a group. So it's a multiplicative group. It's a multiplicative group. Is it abelian? It's not necessarily abelian, because we know that multiplication in general is not, in matrices is not commutative in nature. So let us just construct out an example. So for example, you take, if you take this matrix, let's say 1, 1, no, it won't work. Suppose 2, 1, 0, 3, let's say, and suppose you take 1, 1, 1, 1. Let me check whether it holds or not. If it does not hold, then I'll give it an exercise for you to find two matrices which do not commute in terms of multiplication. So it's 2 times 1 plus 1, 1 times 1, so it's 3. 2 times 1 plus 1 times 1, it's 3. And so it's 0 times 1 plus, so it's 3. And it's 0 times 1 plus 3 times 3, so it's 3. Okay, I hope it won't work. I don't think it will work, but nevertheless, let's see. So it's 1 times 2 plus 1 times 0. It will work. Okay. 1 times 1 plus 1 times 3, 4. 1 times 2 plus 1 times 0, 2. 1 times 1 plus 1 times 3, 4. Thank you. Thank God. It won't work. Yeah. So it's not commutative in general. Okay. Fine. Now let me give a very important example of groups. This is very important example. We will be working out with this example a lot later though. Let me decrease the pen thickness a bit. It's a very broad. Nevertheless, let A be a symbol. So this is a very important statement which seems to be very simple in nature, but it's a very strong statement. Let A be a symbol. So I'm not attaching any meaning to A. A is just a symbol, a notation. A is just a symbol. Consider the set. Consider the set. So what we do is that we take 1. Again, 1 has no meaning attached to it. We'll see how 1 works. So consider the set 1, A, and then keep multiplying A to itself. Okay, keep multiplying A to itself. So I'll get A squared. So I'm abiding by the usual notation. Though again I'm repeating, I'm attaching no meaning to anything I'm using here. Then I'll multiply A to A squared, so I'll get A cubed. I'll do it with A to the power 4. And I'll keep continuing this. So what will I typically get? So I'll get an infinite set which contains only powers of A, right? Such a group, so this will form a group. I'm telling you the reason, it's very simple. See, any two elements in this set is of the form A to the power and A to the power S. So if you multiply them out, again with the usual sense of multiplication, you will get A to the power R plus S, which should also be an element here itself by the way we have constructed out this set. Associativity is trivial in this case. 1 will act as my identity element here. 1 will act as my identity element here. Right? 1 will act as my identity element here, because if you take anything, any art A to the power R times 1, you will get back A to the power R. So you'll get the identity element here. But there's a slight problem again. We are not getting something inverse because, adding two elements, multiplying two elements won't result in 1. So what we can try and do is that we can include the negative powers. So I can take A inverse, A to the power minus 2, A to the power minus 3, and so on. Right? So we take all natural powers of A and all negative integer powers of A as well and construct out this particular set. Now we will readily have inverses, right? So I have A to the power R times A to the power minus R to be 1 in the most usual sense. In fact, this is also an abelian group because this particular multiplication is commutative, because natural numbers are integers are commutative in nature with respect to addition. So this forms a group. Now this is what we call, so this is something which we denote as this. This is called the, so I should also mention it like this. Order of A is infinite. We'll come to this. What does this mean? So this is called the infinite cyclic group. Infinite cyclic group. This word cyclic is what carries the most strength. So it's an infinite cyclic group. Now what do we mean by an order of an element? Later we will see that this infinite cyclic group has a natural group structure exactly like the integers. So we'll see this later, that this is isomorphic. We'll come to a detailed lecture on isomorphism. So it's isomorphic to integers or isomorphic to Z with respect to the usual addition. What do we typically mean by isomorphism? I'm just giving a very brief idea about it. So, okay, so for giving the brief idea, let me just introduce one more thing. What is the order of an element? Okay, so definition. Let G be a group, and in general we will always be undergoing the group operation to be multiplicative in nature. So let G be a group. We say order of A in G denoted as O of A is n is a natural number if n is the smallest positive integer such that A to the power n is identity. Okay. If no such n exists, we say order of a. Now often we take it to be 0 or we take it to be infinity as well, so it doesn't matter. You can also perceive this to be infinity. Okay, rather we'll go with 0. Okay, so let me pose this to be 0. We'll go with 0. So order of the element is 0. Is it clear? Okay, now observe the following. Now let G be a group and let A be an element of G such that order of A is n. Okay, such that order of A is n. Then consider this particular subset of G. This will always be a subset of G, right? Because G is closed under multiplication. So all the elements A squared, A cubed, they are all elements of G. So this is a subset of G, right? So A, then A squared, A cubed, A to the power 4, so on and so forth, A to the power n minus 1. None of these elements are 1, right? Because n is the smallest positive integer such that A to the power n is 1. And then A to the power n is 1, and then so this is the same number of it, so the same elements repeat, so this is the set. Now is it a group? It's surely a group, right? Because any two elements, if you take from here, you multiply them out, you will get a power of A, where the exponent will always be something between 0 and n minus 1, rather 1 and n minus 1, right? Moreover, I am giving you a very brief exercise. Check that all the elements A squared till A to the power n minus 1 are distinct. Okay. So once we have proved this, what we know that the cardinality of this particular set is n, which also was the order of A. Such a subgroup, so it's called a subgroup of G. It's a subgroup of G. That is a substructure of G, which is also a group with respect to the same operations on G. Okay. So it's a subgroup of G. Moreover, by our previous convention, this is a finite cyclic group. This is a finite cyclic group. Okay. Let us draw the Cayley table for this group. Okay, let us draw the Cayley table for this group. So I have right. So let me just take a brief example. Suppose order of A is 5. So yeah, so let us draw the Cayley table. So if you do not know what a Cayley table is, then you will be readily able to understand it by what we are doing here. So we will take the 5 elements at the top, and then we'll take the 5 elements at the bottom. Okay. Here I'll denote the operation. So here I have 1 A squared, A cubed, A to the power 4, and here also I have 1 A squared, A cubed, A to the power 4. And what we'll do is that we'll fill in these grids by multiplying, or rather operating on each of the elements which intersect at the grid. So here we have 1 times 1 1, 1 times A, then 1 times A squared is A squared, 1 times A cubed is A cubed, 1 times A to the power 4 is A to the power 4. Then A times 1 is A times A is A squared, A times A squared is A cubed, A times A cubed is A to the power 4, A times A to the power 4 is A to the power 5, but 5 is the order of A, so it's 1. And similarly, this will be A squared, A cubed, A to the power 4, then here I'll get 1, and here I'll get A. And then I have A cubed, A to the power 4, 1, A squared, and then here A to the power 4, 1, A squared, A cubed. Now take the next example. So this is the last example we are dealing with in this particular lecture. integers modulo n. Now here we are gonna just state the example, but the main motivation behind this particular example will be we will be dealing with this in some other lecture. So what we do is that we take Zn. This is the notation we will be using, and this consider all the elements 0, 1 till n minus 1 with respect to addition modulo n. That is, a plus b is in the sense that a plus b modulo n. Okay, let us understand why this example. So consider Z5. So what are the elements in Z5? It should be 0, 1, 2, 3, 4. And let us understand the group structure via again the Cayley table. So last time I should be making this a bit broad this time. So 2, 3, 4. Yeah, so 0. Oh, no, I need one more space, right? And here I have 1, 2, 3, 4. Okay, so I need a bit broader, right? Yeah. So okay, and this, yeah, this will work. So now here we have addition modulo 5. So here I have 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Now let's add them up, keeping in mind modulo 5. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. It's fine. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, but 5 is 0 modulo 5. 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, which is 0 modulo 5, 2 plus 4 is 6, which is 1 modulo 5. 3 plus 0 is 3, 3 plus 1 is 4, 3 plus 2 is 5, which is 0 modulo 5, 3 plus 3 is 6, which is 1 modulo 5, and 3 plus 4 is 7, which is 2 modulo 5. 4 plus 0 is 0, 4 plus 0 is 4, 4 plus 1 is 0, 4 plus 2 is 1, 4 plus 3 is 2, and 4 plus 4 is 3. Can you see a correspondence between the elements of both these Cayley tables? In fact, while I was writing it out, I hope you also considered that the pattern is quite similar. Something which you can observe here is that the element here which corresponds to a cube, this in some sense behaves the same as the element 3 here. A to the power 4 here acts in the same way like 4 works here, isn't it? So what we can in some sense conclude is that the underlying structure of these modulo groups is in some sense the same as the underlying structure of a finite cyclic group. And basically what we'll see later is that Zn with respect to addition modulo n, this is isomorphic to a finite cyclic group of order n. And we'll also see that Z with respect to addition, this is isomorphic to an infinite cyclic group. And in fact, these two theorems completely characterize cyclic groups, because a cyclic group can either be a finite cyclic group or an infinite cyclic group, because after all it's a set. So it's either isomorphic to Zn's or it's isomorphic to Z. So these completely characterize cyclic group. This is also called the fundamental theorem of cyclic groups. Okay, so that's a lot for this lecture. Let's end this lecture here. In the next lecture, we'll start with being more formal about the structure of groups. So meet you guys in the next lecture.